Good morning, student. So this is our third lecture on topic electrostatics, and today's topic of discussion is electric field. All of you are familiar with the electric charge. In your lower classes you had studied what is that electric charge, and in our previous lecture also we had seen the different properties, basic properties of electric charges. Now suppose here we are having some electric charge. When a charge is kept somewhere in homogeneous isotropic medium, then the space surrounding to that charge, the spherical space surrounding to a given electric charge, due to its presence, it gets modified. What happens to the space surrounding to the given charge? It gets modified. And as you know, that between the two electric charges either there exists a force of attraction or there exists a force of repulsion. So here suppose we are having a test positive charge. What I am saying? Test positive charge. Q0 it represent or it is known as a test charge. Now what is a test positive charge? Here onward, everywhere, during the study of electrostatic, everywhere you will heard the name test positive charge. Means this test charge is positive charge, and second thing, the magnitude of this test positive charge is so small so that it will not affect the surrounding of any given charge. What is a test positive charge or what is a test charge? Test charge is positive charge, and number two, its magnitude of test charge is very small, or it is so small so that it will not disturb, it will not affect the surrounding of a given charge. It will not disturb or it will not affect the surrounding of a given charge. So when such test charge is brought near to a given charge, when some test charge is brought near to a given charge, we know that if test charge is far away from a given charge, is there any Coulombian force that will act in between them? No. It means surrounding to given charge, there is a spherical region. Surrounding to a given charge, there is some spherical region with given charge at its center. And in that spherical region, when test charge enters, that test charge will experiences a force. That force may be force of attraction. If this charge is negative charge, that force may be force of repulsion. If both the charges, because this is positive already, if given charge is also positive, then that Coulomb force is a force of repulsion. So remember that when a charge is kept at some point in isotropic homogeneous medium, then surrounding to that given charge, there will be a formation of spherical region which gets what? Modified. The spherical region surrounding to given charge is modified. And in such a modified spherical region, when test charge is brought, test positive charge is brought in the region of what? In the spherical region surrounding to given charge, then that test charge, it will experiences, that test charge will experiences what? It will experiences a Coulomb force. It will experiences what? A Coulomb force. So a region surrounding to or a region around the given charge. This is a region around the given charge in which Coulomb force is experienced by another charge. In which a Coulomb force is experienced by another charge. That region is called what? An electric field. That region is called an electric field. So, whenever you come across the word, what is electric field? The region around the given charge. The region around the given charge object in which Coulomb force is experienced by another charge, that region is called an electric field. That region is called an electric field. But remember, this is what the theoretical definition of electric field. So you always keep in mind, whether charge is positive or charge is negative, there is some spherical region surrounding to positive charge or surrounding to negative charge. That spherical region in which when a test positive charge is brought, that test positive charge, it will experiences a force. It will experiences what? A Coulomb force. That Coulomb force may be force of attraction or it may be force of repulsion, depending upon whether the given charge is positive charge or whether the given charge is what? Negative charge. So, the region around the charge object in which a Coulomb force is experienced by another charge is called electric field. Now, mathematically, one can define the electric field in this manner. Electric field is force per unit charge, force experienced per unit charge or force experienced by test positive charge. Electric field is force experienced per unit charge or force experienced by a test positive charge. It is defined as electric intensity. So mathematically what you can say? Mathematically the force experienced per unit charge is called an electric field or electric intensity. Sometimes this electric field, it may be called as intensity of electric field. It is intensity of what? An electric field. Now let us consider that we are having a charge Q. Let capital Q is a charge and there is another charge Q0 which is at a distance r from a given charge. Q is some charge and another charge is Q0 which is at a distance r from a given charge. Remember here that charge Q0 is kept in the region of electric field produced by this charge. Then according to Coulomb's law, what is the Coulomb force? Coulomb force vector F is equal to 1 upon 4 pi epsilon 0. If I consider that both the given charge Q and Q0, they are kept in free space or in vacuum, then here 1 upon 4 pi epsilon 0, that constant of proportionality K is 1 upon 4 pi epsilon 0, and the product of magnitude Q0 divided by square of distance of separation between them into that unit vector r cap. Unit vector what? R cap. Now, By definition, what is the electric field? Electric field due to charge q at a distance r from it. Electric field due to charge capital Q at a distance r from it, by definition E must be equal to vector F divided by what? That test positive charge Q0, or it is equal to 1 upon 4 pi epsilon 0 Q0 divided by r square into r cap into 1 upon Q0. So this Q0 get cancelled. Or that electric intensity E is equal to 1 upon 4 pi epsilon 0 Q divided by r square into r cap, where r cap is what? R cap is a unit vector along the line joining the charge Q and Q0, along the line joining charge Q and that of Q0. Remember here, the direction of unit vector, no doubt it is along the line joining charge Q and Q0, but it will act along the direction of Coulomb's force. Along the direction of what? Coulomb force. See here, because force is a vector, electric intensity is also a vector. The direction of electric intensity is same as that of direction of what? The Coulomb force. Direction of electric intensity is same as that of what? Direction of what? Coulomb's force. Remember here that as far as electric intensity is concerned, that electric field, every charge will produces its own electric field. Suppose we are having a charge Q. A given charge produces its own electric field to its surrounding irrespective of presence of any other charge. Means in the region of electric field produced by this charge, there might be some another charge Q0. Irrespective of this charge Q0 or Q1 or Q2, this charge will produces its own electric field. And Coulomb's force will not require any material medium for their intervening. It will experience even when charges are kept in, or when charges are kept in what? Free space or in vacuum. Charges are kept in free space or in vacuum. Now let us try to calculate what is the magnitude of electric field at a distance r from the charge Q. Suppose we are having a charge Q kept somewhere at point O, and we want to find out what is the intensity of electric field, or what is electric field at a distance r from the charge Q. Electric field due to charge Q at a distance r from it. It is found to be same for all the points which are at same distance r from it. Means we can have a locus of all such points of the media surrounding to given charge Q which are at a same distance r, then it is a spherical region. So a sphere of radius r, Every point on that spherical region, they are at same distance r from the charge q. And remember, electric intensity at every point on the sphere of radius r due to charge q, everywhere it is same. And what is the magnitude of that electric intensity? E equal to F by Q0, and as we had calculated, it is equal to 1 upon 4 pi epsilon 0 Q divided by R square into what? R cap. So this is vector form, and in magnitude it is 1 upon 4 pi epsilon 0 Q divided by R square. So remember that you can imagine now that whenever you were given a charge q and you have to calculate what is the electric intensity at any point at a distance small r from it, then that electric intensity it is given by formula 1 upon 4 pi epsilon 0 q divided by what? R square. Q divided by R square. Now, as far as the direction of this electric intensity, see here, the direction of electric intensity, no doubt this electric intensity, it will act along the radius. Electric intensity will act along the direction of what? Coulomb force. Coulomb force will act along the line joining given to charge. Line joining what? Given to charge. So remember, because electric intensity it acts along the Coulomb force between the two charges, that Coulomb force it will act along the line joining the given two charges. That's why electric intensity or electric field, it will also act along the line joining given charge, or it will act along the radius. And remember that electric intensity is radially outward in nature. What I am saying, radially outward means that electric intensity it will act along the radius of a spherical region surrounding to given charge, and it is pointing in outward direction only when that charge is positive charge. So any positive electric charge produces a spherical region to its surrounding, which is called as an electric field, and that electric field, it is a vector, it will act along the radius and it is directed in outward direction if that charge is a positive charge. So a positive charge produces radially outward electric field. Similarly, if that charge is a negative charge, no doubt that electric field, definitely it will act along the radius. But it is radially inward. So whenever charge is negative charge, electric field will act along the radius, but its direction is what? Inward, that is towards the charge. So the 2 points that you have to remember, that positive or negative charge both will modify their surrounding space, so that when test positive charge is brought in that surrounding space, that test positive charge, it will experiences a Coulomb force. So that spherical region surrounding to any charge object which experiences, or in which a Coulomb force is experienced by some another charge, that region is called electric field. Mathematically, that electric field is nothing but force per unit charge. Force per unit charge. Remember, whenever we have to find out the electric intensity, we always make use of a test positive charge. What is a test positive charge? It is a positive charge whose magnitude is so small so that it will not affect the surrounding of a given charge. So electric field can precisely be defined as the force acting on, I will read it, a force experienced by a test positive charge, force experienced by a test positive charge in presence of a given charge. Force, Coulombian force experienced by a test positive charge in presence of a given charge at a given distance. In presence of a given charge at a given distance is called electric field. What is electric field? Electric field is the Coulomb force experienced by a test positive charge in presence of a given charge at a given distance. Means you can define electric intensity is equal to limit Q tends to 0, means the magnitude of that test positive charge is very small, so that it will not affect the surrounding of a given charge, into vector F divided by Q. Vector F divided by Q. Electric intensity, it is the Coulomb force experienced by a test positive charge. Coulomb force experienced by a test positive charge in presence of a given charge at a given distance. And how you will define the test charge? Test charge is a positive charge whose magnitude is so small so that it does not affect the surrounding of a given charge. Surrounding of a given charge. Now, as far as SI unit of electric intensity is concerned, SI unit, now you know that E is equal to F by Q. Also, in your lower classes, you know that electric intensity is negative of potential gradient. Potential gradient, potential is denoted by a letter V. Gradient means when V is, or the change in potential with change in distance is called potential gradient. So E is equal to negative of potential gradient. See here, E equal to F by Q, E equal to V by X. Force is measured in Newton, charge is measured in Coulomb. Potential is measured in volt and distance or displacement is measured in what? Meter. So Newton per Coulomb or volt per meter are the SI unit of electric field. Electric field can be measured either in SI unit of Newton per Coulomb, or sometimes it can be measured in the unit of what? Volt per meter. So this is all about the basic idea regarding electric field. In short, in 2 or 3 lines we can define: every charge produces a spherical region to its surrounding, in which when a test positive charge is brought, that test positive charge will experiences a Coulomb force. That spherical region in which a test positive charge will experiences a Coulomb force is called an electric field. Mathematically, it is a force per unit charge. Coulomb's force is given. Suppose we are having a charge Q, test charge Q0 kept at distance R, then Coulomb force is given by expression 1 by 4 pi epsilon 0 Q0 upon R square into unit vector R. So this R cap represent a unit vector along the line joining charge Q and Q0. And direction of unit vector is same as that of direction of a Coulomb force. So the electric field due to charge q at a distance r, it is given by F by q0, 1 upon 4 pi epsilon 0 q divided by r square into r cap. Remember, because Coulomb force is a vector, electric field is also a vector, and the direction of electric field is same as that of what? Direction of what? Coulomb force. Now, to find out what is the magnitude of electric field due to charge q at all the points which are at a distance r from it. It is a sphere. So, electric intensity at every point on a sphere of radius r. At its center, charge q is kept. That electric intensity at every point on that sphere of radius r, it is given by 1 upon 4 pi epsilon 0 q divided by r square. This is the magnitude of electric intensity at every point on the sphere, and everywhere it is found to be what? Same. Remember that as we told you that electric field is a vector. So, electric field will act along the radius of that sphere. If charge is positive, it is outward in nature, means for positive charge, electric field is radially outward. For negative charge, electric field is what? Radially inward. And as far as SI units of electric field is concerned, it is E equal to F by Q, means Newton per Coulomb, or E equal to minus dV by dx, that is negative of potential gradient. Therefore, volt per meter is also SI unit. Now, you can find the dimensions. What are the dimensions of force? L1, 1 in length, 1 in mass, minus 2 in time. What are the dimensions of charge? From the definition of current, I equal to Q by T. So, Q is equal to I into T. So, the dimensions of charge are I1, T1. So, the dimensions of electric intensities are, or electric field are 1 in length, 1 in mass, minus 2 in time, minus 1 in I, and minus 1 in time. Again, means it is minus 3 in time. So, the dimensions of electric field. What are the dimensions of electric field then? 1 in length, 1 in mass, minus 3 in time, and minus 1 in I. These are the dimensions of electric field. Now, let us calculate the electric field intensity due to a point charge, but in what? In material medium. So, let us consider that we are having some charge q which is kept in an isotropic homogeneous medium at some point O. A point charge q is kept at point O in an isotropic homogeneous medium whose dielectric constant is K. What is the dielectric constant of a medium? Already we had studied the dielectric constant of medium. It is a ratio of absolute permittivity of a medium to the permittivity of free space, or sometimes it is also known as relative permittivity of a medium. So, a charge q is kept at point O. What this charge will do? The spherical region to its surrounding, it gets modified. Means that charge will produces an electric field to its surrounding. Suppose we are having a test positive charge Q0. We are having what? A test positive charge or a test charge Q0. Here Q0 is what? It is a test charge. What is a test charge? Test charge is a positive charge and its magnitude is so small so that it will not affect the electric field surrounding to a given charge. So a test positive charge is brought in the region of electric field produced by a charge q, and let that test charge is at a distance r from the given charge q. So situation is clear that we are having a given charge q which is kept in a surrounding, that a media is having dielectric constant K, a test charge Q0 is kept at some point P in the region of electric field produced by charge Q at a distance r from it. We know from the basic properties of electric charge that whenever two charges they are brought near to each other, then they will experience a force. So here between the two charges Coulomb force will act, and according to Coulomb's law, the Coulomb force between given charge q and test positive charge q0, force experienced by test positive charge due to charge q according to Coulomb's law is F equal to 1 upon 4 pi epsilon 0 into K. Here, instead of writing epsilon 0, because every now and then while using Coulomb's force we will make use of epsilon 0, because we are assuming that the charges were in free space or in vacuum. But purposely here, charges are kept in material medium whose dielectric constant is K. Therefore, the Coulomb's force between the charge Q and test positive charge Q0, that is, the force experienced by a test positive charge is 1 upon 4 pi epsilon 0 K, because K is dielectric constant of medium, into the product of magnitude of charge q0 divided by r square into a unit vector r cap. Here r cap is what? R cap is a unit vector. R cap is a unit vector. It acts along unit vector. It acts along what? OP. That is, R cap, it acts along the direction of Coulombian force. Direction of what? Coulombian force. Now, by definition, what is the electric intensity due to charge q at a distance r from it? Electric intensity due to charge q at a distance r from it is E equal to F divided by q0, or we know the Coulombian force 1 upon 4 pi epsilon 0 K q0 divided by r square into r cap into 1 upon q0. So this test charge get cancelled, and the electric intensity due to charge q, due to a point charge q is what? A point charge. So electric field due to point charge q at any point P at a distance r from it, which are kept in what? A material medium, is E equal to 1 upon 4 pi epsilon 0 K q divided by r square into r cap. So this is what we are expecting. This is an expression for electric field due to point charge in what? In a material medium of dielectric constant K. In a material medium of dielectric constant K. See here, The direction of electric field is same as that of direction of what? Coulomb force. The direction of electric intensity, the direction of electric intensity is vector E will act along OP, if that charge Q is positive, because if this charge is positive, we know the force exerted by a positive charge on a test positive charge, here that test positive charge will experiences what? A Coulomb force, which will act away because it will exert a force of repulsion. It means the direction of electric intensity is also same, because E equal to F by Q0. Whatever may be the direction of force, same is the direction of electric intensity. So this electric intensity or electric field E, it will act along OP when the charge Q is a positive charge. Already Q0 is what? Q0 is a test positive charge. Q0 is what? A test positive charge. Whereas vector E, it will act along PO. Here the direction of E will be opposite PO. When that charge Q is a negative charge. When that charge Q is what? A negative charge. So in examination there might be a question for 2 mark. Define electric field. What is electric field? The spherical region surrounding to a given charge in which a Coulomb force is experienced by any other charge is called electric field, or electric field is nothing but force experienced per unit charge. And as far as electric field intensity due to point charge is concerned, if I consider any point charge Q which is kept in a medium of dielectric constant K, and let that charge Q produces its own electric field, and in the region of electric field, if a test positive charge Q0 is brought at point P which is at a distance r from it, then between the two charges Coulomb force will act, and it is given by formula 1 upon 4 pi epsilon 0 K Q0 upon r square into r cap, where K represent dielectric constant of that medium. R cap, it is a unit vector along OP, it will act along the direction of force. Then the electric intensity by definition, it is force experienced per unit charge. So it is found to be 1 upon 4 pi epsilon 0 K Q upon r square into what? R cap. This electric intensity, it is a vector quantity and it will act along OP. Its direction is along OP. If charge is positive, its direction is along PO. If this charge is what? Negative. In general, the magnitude of electric field due to charge Q, magnitude of electric field due to charge Q at a distance r from it is 1 upon 4 pi epsilon 0 K, when that point charge is kept in a material medium of dielectric constant K, is E equal to 1 upon 4 pi epsilon 0 K Q divided by what? R square. So this gives you the magnitude of electric field due to a point charge kept in a material medium of dielectric constant K, of dielectric constant what? K. Now after knowing this magnitude of electric field, if I say that material medium, instead of material medium, if I take that media itself is air, for air, relative permittivity or a dielectric constant K for air, it is equal to what? 1. Why? Because K equal to epsilon divided by epsilon 0. And epsilon, permittivity of medium, permittivity of air or free space or vacuum, it is epsilon 0 upon epsilon 0, so it is equal to 1. Therefore, electric field due to charge Q, electric field intensity, electric field intensity due to a point charge in air is 1 upon 4 pi epsilon 0 Q divided by R square. This is the magnitude of electric field. Magnitude of what? Electric field intensity due to point charge in air. Remember here, as far as Coulomb's force or electric intensity or intensity of electric field is concerned, see here, the Coulombian force, what you can say, that the force, Coulomb force between the two charges, they are inversely proportional to square of distance of separation between the two charges, and the electric intensity due to a charge at a distance r is inversely proportional to square of its distance between given charge and that point. Means both the force and electric intensity both will obey inverse square law. Coulomb force and electric field intensity both will obey inverse square law. It means if we try to plot a graph of electric intensity or Coulomb force against the distance r, then as they obey inverse square law, that graph must be what? Exponentially decay in nature. That graph must be what? Exponentially decay in nature. Same is the case with gravitational force between the two particles of the media. So, electric field intensity or Coulomb force between the two charges, as both will obey inverse square law, so their graph between E or F against that of R, it is exponentially decay in nature. Now we will see what do you mean by a uniform electric field and non-uniform electric field. Let us now see what is a uniform electric field and non-uniform electric field. Quite simple. The field whose magnitude as well as the direction is same. The electric field whose magnitude as well as the direction is same at all the point, it is called uniform electric field. While the electric field whose magnitude as well as the directions, they are not same at all the point, it is called non-uniform electric field. Remember carefully, the electric field whose magnitude as well as direction is same at all the points is called uniform electric field. So, where such type of uniform electric field is produced? So, suppose we are having two metal plates which are kept parallel to each other and close to each other, and let the two plates are given. One of the plate A is given positive charges, other plate B is given negative charges. We know that positive charge will produces an electric field to its surrounding, and the direction of electric field due to positive charge is directed away. Means whatever positive charges they are deposited on plate A, they are producing the electric field which is pointing away from it. Similarly, if we are having a negative charge, then the electric field due to negative charge, it is pointing towards that negative charge. So on the plate B, where we are having what? Negative charges. So the direction of electric intensity due to negative charges, it is directed towards the plate. From positive charge, electric field intensity is pointing away. On a negatively charged plate B, how is the direction of electric field intensity? Due to presence of negative charge, that E is directed towards the plate B. In general, we can say, in a space between parallel metallic plates which are charged in such a manner that A is positively charged, B is negatively charged, then in a space between the two charged parallel plates, a uniform electric field of intensity E is produced, and the direction of electric field intensity, it is always from the plate at positive charge towards the plate at a negative charge. Means, in any case, suppose here this plate is positively charged and this is a negatively charged. In a space between two plates, electric field is produced. And the direction of electric field intensity, it is always directed from what? Positively charged plate towards the negatively charged plate. So, the electric field in a space between two parallel charged plate is uniform electric field. It means, if I measure the electric field intensity either at point P or at point Q or at point R, P, Q, R, these are the different points in a space between the two charged parallel plates. Remember, intensity at every point, their magnitude must be what? Same. At every point, the direction of electric intensity, it is also what? Same, towards negative plate. So, as the magnitude of electric intensity at any point in a space between two parallel plates which are being charged, as magnitude of electric field intensity is same as well as their direction is same. So, one can conclude that a space between parallel charged plate will consist of uniform electric field. Now, non-uniform electric field, an electric field whose magnitude as well as the directions at all the points are not same. Such electric field is called non-uniform electric field. We know very well that when we are having some charge, that charge may be positive or that charge may be negative. Every charge produces electric field to its surrounding. And if I just try to draw a test positive charge, if that test positive charge is kept somewhere here, it gets repelled because it is in the region of electric field produced by a positive charge. If I just try to place that charge Q0 very close to charge Q, then the force of repulsion will be more. Here force of repulsion is somewhat less because it is at somewhat longer distance from charge Q. Means, when I try to bring a test positive charge near and near to given positive charge, that test positive charge will experience as what? More and more force. It means, from definition, E is equal to F by Q0, or the force experienced by a test positive charge is equal to E into Q0. Q0 is same. So, here at the nearer point, that test positive charge will experiences a more force of repulsion. It means electric intensity near to a given point charge is more, and that intensity of electric field or electric field intensity, it goes on decreases as we move away from a given charge. Means the electric field produced by a charge is non-uniform. That given charge will produces a spherical region to its surrounding, and in that spherical region test positive charge will experiences a Coulomb force. That Coulomb force will be stronger when test positive charge is brought near to that given charge. It will be weaker when test positive charge is what? Somewhat at a longer distance from given charge. So remember, an electric field produced due to a point charge, electric field produced due to a point charge is always non-uniform electric field, because if I try to measure the electric field at a point P which is near to that of given charge, electric intensity, its magnitude is large. There is some another point Q which is somewhat at a greater distance from given charge. The magnitude of electric intensity at point Q, that is away from given charge, is less as compared to that of at point P. Means magnitude of electric intensity is different at different points, as well as the direction of electric intensity at point P will be here. The direction of electric intensity at point P will be in somewhat other direction. Means whatever field is produced by a point electric charge, that electric field produced by a point electric charge, it is non-uniform because of both the magnitude as well as what? Directions at different points are found to be different. But remember here, you may have a situation, suppose that we are having a sphere of some radius r. Every point on a sphere of radius r, they are at what? Same distance r from a given charge, and we know that electric intensity E is equal to 1 upon 4 pi epsilon 0 k q divided by what? R square. Means E is inversely proportional to R square. So all the points which are at a same distance r from a given charge q, magnitude of electric intensity definitely it is same, but their directions are different at different point. So that's why we can say electric field intensity, it is different at different point. Means a point charge produces electric field. If that point charge is positive charge, that electric field is radially outward. Magnitude of electric field intensity at all the points which are at a distance r from it, magnitude of electric field, no doubt it is same, but their directions are different at different points. And because both magnitude as well as the direction of electric field at all the points surrounding to given point charge is not same, so we can conclude the electric field produced due to a point charge is non-uniform electric field. So do you understand? Now, how to calculate the electric field? So suppose we are having two metallic plates A and B. They are kept parallel to each other. They are kept close to each other, means they are separated by a distance d. Let plate A is given positive charges, plate B is given negative charges. Then we know how is the direction of electric field. As A is given positive charge, B is given negative charge, that's why the direction of electric field intensity, it is pointing from plate A towards plate B, and because E is equal to F divided by Q, direction of electric intensity is same as that of what? Direction of Coulomb force. If I say that V is the potential difference applied between the two parallel metallic plates which are positively and negatively charged, because this plate is at positive potential, it has some potential. Plate B is given negative charges, means it has some potential. If I say that V1 is potential of A, V2 is potential of B, then V1 minus V2 equal to V is equal to potential difference between the two plates. So we are having the two parallel metallic plates A and B. A is given positive charge, B is given negative charge, and V is the potential difference between them, and small d represent the distance of separation between them. You know very well that the electric field in a space between parallel charge plates is uniform. So here also a uniform electric field is present. Let us consider that we are having some charge Q. Let charge Q is kept at some point P. P is some point where that charge Q is situated. And if I want to move that charge towards the plate A, that charge is acted upon by, because that charge, it is acted upon by Coulomb force. What is the direction of force acting on that plus Q charge? So when plus Q charge is kept at some point P in a space between two charged parallel plates, that charge is acted upon by Coulomb's force F. And what is the direction of this force? It is same as that of direction of electric field intensity. That electric field intensity is acting from plate A towards plate B, means that charge is acted upon by electric field intensity, and I want to move the charge against the Coulomb force, against the direction of electric intensity. I want to move plus Q charge towards the plate A, means I have to move the charge against the direction of electric field or against the direction of force. It means I have to do some work to move the charge towards the plate A. Some small amount of work must be done to move the charge, and if I say that dW is that small amount of work that must be done against the force F in order to move the charge through a small distance dx. This distance is dx. What is the maximum displacement that a positive charge can have? Remember, when I wish to move the charge plus Q from a negatively charged plate B to a positively charged plate A, what I am saying, I want to displace plus Q amount of charge from plate B towards plate A. B is negatively charged, A is positively charged, because on that charge force is acting towards plate B, but we want to move the charge towards plate A, means we have to do some work against that Coulomb force. And what is the total work that we have to do? The total work done to move plus Q charge from plate B towards plate A. What is the displacement of that charge? Displacement of charge is D. Work is done against the Coulomb's force F. So work done is equal to force into displacement F, Coulomb's force. Displacement, what is the displacement? We want to move the charge from plate B towards plate A. So that charge undergoes a displacement equal to what? Distance between the two plates. So work done equal to force into displacement. But by definition, work done, if V is the potential difference between the two plates, V is the potential difference between the two parallel metallic plates which are being charged. A is positively charged, B is negatively charged, and they are separated by a distance d. They are what? Separated by a distance V. You know, in 10th standard you had studied that potential difference is always equal to the amount of work that must be done in order to move a charge from infinity to that point. So V equal to W by Q, potential difference is equal to work done upon charge, or W is equal to V into Q. This is equation number 2. Now we are having the two expression for work done. One is force into displacement and other is what? Potential difference into what? The amount of charge which is to be displaced. Now you can equate the right hand side. So F into D is equal to V into what? Q, or F divided by Q is equal to what? V divided by D. But we know by definition, already we had defined electric intensity is nothing but force experienced per unit charge. Electric intensity or electric field intensity is nothing but force experienced per unit charge, but this is also equal to V by D. What is V? Potential difference. What is D? The distance between the two plates. V by D combinedly it is called as a potential gradient. So electric field intensity, now it can be defined in a two different way. The first definition of electric field intensity, it is a force experienced per unit charge is called electric field intensity, or one can also define electric field intensity is nothing but potential gradient, that is potential difference per unit what? Distance. Potential difference per unit distance or potential gradient, it is also defined as the electric intensity. So that's why whenever we are talking about SI unit of electric field intensity, for F by Q, force is measured in Newton, charge in Coulomb. So Newton per Coulomb is SI unit of electric field intensity, or because it is a potential gradient, potential difference is measured in volt and distance is measured in what? Meter. So that's why SI unit of electric field intensity, either it is Newton per Coulomb or it may be what? Volt per meter. So you remember what is uniform electric field and non-uniform electric field. The electric field whose magnitude as well as the directions are same at all the points is called uniform electric field, and that is possible in case of what? Two charged metallic plates which are kept parallel to each other, and the space between those charged parallel metallic plate, it consists of uniform electric field. Non-uniform electric field, the electric field in which both magnitude as well as the direction at all the points are not same, they are different. The electric field produced by a point charge to its surrounding, it is spherical in shape. Electric field at a different point, their magnitude is different, their direction is different. So that's why field produced by a point charge is a non-uniform electric field. You may have a situation that if I just consider all the points which are at same distance r from the given charge, no doubt the magnitude of electric intensity at every such point which are at same distance are, magnitude of electric intensity is same, but their directions at different points are different. Naturally, electric field is different at different point. So the field produced by a point charge is non-uniform electric field. And practically, to determine the electric field, that electric field is calculated by using the formula V divided by D, means find out the potential difference between the two plates and the distance of separation between the two plates. That will give you electric field intensity. So electric field intensity, either it is force experienced per unit charge, or it is what? Potential gradient, potential difference per unit distance. SI unit of electric field intensity, either it is Newton per Coulomb, or it is what? Volt per meter, or it is volt per meter.